one interesting thing about you compared with many science writers, not that they aren't interesting in their own right, is that you do look at the larger picture. You look at the intersection of science with philosophy, with religion, with aesthetics, and that brings up questions about, the connection between science and the mind and consciousness, and the limits of science. Does science have limits as a mode of inquiry, and so on? All the deep philosophical issues tend to come up in your work, and so I'm very happy we're going to have a chance to get to as many of these as possible. But let me start out with one of your more recent and offbeat sounding initiatives, which is that you co-founded with your identical twin sister something called the Institute for Figuring.
Yes.
Is that now that demands explanation, and I think you're the one to do it, not me.
Well, the Institute for Figuring, you'll probably recognize as a science person, Bob, that its acronym is if and only if, which is the logical symbol. Sorry, its acronym is IFF, which is the logical symbol for if and only if. And we like this name because figuring is a word that connotes many different disciplines. So figures are numbers, figures are mathematical diagrams. We all have a figure, which artists draw figures. And of course, we're all constantly in the process of figuring things out. The mission of the Institute for Figuring it comes out of my work as a science communicator. Basically, what I want to do is to use the Institute for Figuring as a way to engage people creatively with science, mathematics, and engineering subjects, but through processes that are often more affiliated with the arts, such as getting people to build stuff. Mm-hmm. And the whole initiative was basically precipitated by the fact that about 10 or 12 years ago when I started the Institute, I myself felt that science communication had become a bit limited. If you looked at who reads science magazines, which I did a lot of research on this one about that time, it's basically, in a nutshell, well-off white men over 40, which is not a value judgment at all. It's just a statistic.
Some of my best friends fit that demographic, I must say.
Some of mine too. But I think that we need more ways of reaching out to more sectors of our society. And indeed, lots of men don't read science magazines. So I started this organization to basically do science communication in a more creative and, as it were, artistically inflected way.
Okay. And so you're right. It's a very multifaceted word, figuring. I mean, the facets kind of intersect, right? Because, I mean, when you look at figures in the sense of physical structures,
yes,
there's often a mathematics implied by them or evident in them, which brings up the word figuring in the sense of mathematics, right?
Yes.
And then there's often, in turn, a relationship, like if you're looking at biological structures, like that exhibit regularity, like coral reefs or various other things, the kind of mathematical regularity they embody in turn reflects something about physical law and the law, and maybe the laws of physics governing their environment, like, things like water pressure that they have to cope with or whatever. I mean, is this making sense?
Yes. So one of the projects that we do, which is the thing that we're most well known for, is my sister and I began 10 years ago a project to crochet a coral reef. And we now work with communities all over the world. We've literally worked in a dozen countries in 40 different cities on building these community reefs with people from everywhere from New York and London and Sydney to Abu Dhabi. And the project comes from the fact that when you see coral reefs and the frilly crenellated structures they make, those structures are biological manifestations of a kind of mathematics called hyperbolic geometry, which is an alternative to the Euclidean geometry we learn about at school. And a wonderful thing is that although human mathematicians spent hundreds of years trying to prove that hyperbolic structures were impossible, nature has been doing it, particularly in the sea, for hundreds of millions of years. And it turns out that although brainless corals and brainless kelps can easily make hyperbolic structures, it's quite difficult for humans to actually make models of this. But in 1997, a mathematician at Cornell, Dr. Dana Taimina, discovered that you could do it with crochet, which was pretty amazing. And with the crochet models, you can stitch theorems onto the surface and show that things like parallel lines and triangles behave differently in hyperbolic space than they behave in Euclidean space.
Now, can I it's been a while since I took geometry, decades and decades. Is Euclidean geometry, is it confined to 2 dimensions or confined to 3 dimensions? It's
Good question. So you can have Euclidean geometries in any number of dimensions. But let's just restrict ourselves for the discussion at the moment to 2 dimensions. So, we learn Euclidean geometry at school, and we just, learn about, we can draw the Euclidean figures on the surface of a piece of paper. So let's just stick to 2 dimensions, and I can talk about 3-dimensional case in a bit. So in a flat piece of paper, that's 2 dimensions. And you can draw parallel lines, and the quality of parallel lines is they stay the same distance apart forever. And you can draw triangles, and one of the qualities of triangles is that they always have all triangles, the interior angles add up to 180 degrees.
Right.
But those 2 things that I've just told you are not true on the 2 other geometries that we know of. So the 2 other kinds of geometry that we have, one is spherical geometry, which is the surface of the Earth. Mm-hmm. And think about what you know about the surface of the Earth. If you look at the lines of longitude where they cross the equator, they're all parallel to one another.
Right.
But yet they come together at the North and South Pole.
Right. That's what I had in mind when I naively said, is it confined to 2 dimensions? I was remembering that when you get to the surface of the globe, it's not Euclidean, but you're right. That's not because it's 3-dimensional per se. It's because the surface itself, you're dealing with a surface, and the surface is not flat.
That's right. The surface itself, and you're putting it very well, the surface itself is 2-dimensional, even though the shape overall appears from the outside to enclose a 3-dimensional space. But from what mathematicians have a way of naming this, they say that it is intrinsically 2-dimensional. So from the point of view of a critter living on that surface, they're only aware that they live on a 2-dimensional surface, even though they could walk around their surface and come back to where they started, and therefore they would be able to tell that they lived on a sphere rather than a flat surface, which is effectively what we humans figured out at some point a couple of thousand years ago. Mm-hmm. The Greeks figured out that we lived not on a flat surface, but on a spherical surface.
Okay, and so this crocheting project, is this like 3-dimensional? Well again, no, it's crocheting. It's crocheting. Well, you tell me what it is.
Well, okay, so if you think about a flat surface like a sphere, a flat surface like the Euclidean, you think about the Euclidean plane as a flat surface, and if you kind of wrap it up on itself, you can imagine turning it into a sphere by kind of wrapping it up around, attaching itself to each other. But imagine that I did the opposite. Imagine I took the flat surface and kind of moved everything, stretched everything and made it move away from itself. Well, that's the structure that's called a hyperbolic plane, and geometrically it's the opposite of a sphere. You shouldn't worry if you're feeling bamboozled by this, because frankly, the greatest mathematicians in our culture felt bamboozled by it, and in fact were nearly driven mad by trying to understand this structure. But here's a nice way of thinking about it. If you think about the flat Euclidean surface, it has no curves, so it's technically classified by mathematicians as having 0 curvature. You can look at a sphere and say, it's got a different kind of curvature. Mathematicians call that positive curvature. And so if it makes sense that there's a positive curvature thing, then it sort of makes sense there'd be a negative curvature thing. And that's what the hyperbolic plane is. It's a negative curvature surface. So in a sense, it's like the geometric equivalent of the negative numbers. Okay. Now, there's lots of ways of understanding this, and none of them were intuitively easy for mathematicians. But one way is to just look at the behavior of simple things like parallel lines and triangles on this surface. And in a hyperbolic surface, parallel lines don't always stay the same distance apart. In fact, they get further and further away from each other. And in this surface also, triangles and circles behave strangely. So the inner angles of a triangle add up to less than 180 on a hyperbolic surface. And in fact, in the extreme case, in the biggest possible triangle you can draw, the inner angles of a triangle add up to 0. Now, why does this matter? It matters because the discovery of hyperbolic geometry actually ushered in basically a revolution in geometry, which led mathematicians in the 19th century to really generalize geometry to make it a much, much more powerful system in which they could understand lots more different kinds of structures. And that ultimately led to what's called Riemannian geometry, which is the geometry that Einstein used for the general theory of relativity.
Okay. And you've got people all over the world involved in this crocheting project, and
yes.
and they're aware of the connection to non-Euclidean geometry and the connection to coral reefs?
Yes. So we have people all over the world crocheting corals, and that's because what we do is individual people, sometimes hundreds or even up to 1,000 people in an individual city or state, will crochet corals, and then we bring them all together and assemble them into a vast topography that looks like a living reef, a very large, a large living reef, and that gets exhibited in science museums and art galleries. And the reason that we're doing this in part is not only to teach the people who are doing it about geometry and the foundations of mathematics, but also to draw attention to the plight of coral reefs, which, as you know, Bob, are being devastated all over the world. So the project really has a huge ecological dimension. It's trying to say, look, people, global warming is not something in the distant past, in the distant future. It's here and now. Coral reefs now, scientists are saying just this last month, they may disappear by the end of this century, even before the end of this century. We must try to preserve them.
And I assume if people Google Institute for Figuring and Crocheting, they can get more information about this.
Yes, and they can Google Crochet Coral Reef. We have a huge website. And for those of people who are in New York, there's a very beautiful exhibition of the project on at the Museum of Arts and Design that's just opened. So that's on Columbus Circle in Midtown Manhattan.